So today we are continuing our journey through different approaches for theoretically analyzing the fractional quantum Hall effect. We talked already about trial wave functions and about numerical diagonalization, and we are going to talk now about wire constructions. As you can guess, if there's a long list of different approaches, probably none of them is perfect. Each one of them has its strengths and weaknesses, and the same holds also for the one we're going to talk about today. So the idea of a wire construction is to think about the plane as made of many parallel wires. So the system we're looking at is made of parallel wires forming a plane and subjected to a perpendicular magnetic field. Now, the wires are coupled to one another by tunneling, and this is what makes them into a plane. When an electron tunnels from one wire to another, it gets a momentum from the Lorentz force. And the Lorentz force is EBD, is velocity times the charge over C times magnetic field. So the force the electron gets becomes E, the charge, times the magnetic field B, times D, the distance between the wires divided by the speed of light. Now, in order to analyze the quantum Hall effect, we need also to understand what's the fitting fraction for this system. And for that, we need to have an expression for the 2D density, for the two-dimensional density. So the two-dimensional density is just the one-dimensional density divided by the distance between the wires. And the density within each wire is just the Fermi momentum of that wire divided by pi. So altogether, this is the two-dimensional density, and this is the fitting factor. The fitting factor is expressed here as a ratio of two momentum scales. 2h bar k Fermi, which is basically the momentum separation between the right and left Fermi points of each wire, divided by the momentum that's being given by the Lorentz force. So we'd like to construct, to start with, integer quantum Hall states from this starting point. And the way to do that would be to look at our wires, wire 1, wire 2, wire 3, all the way down to wire million, and to look at them in momentum space. So in momentum space, here's the dispersion, the energy versus the momentum, and you see one wire, second wire, third wire, here the dispersion is quadratic, that make a difference. Now we are going to fill those wires up to the chemical potential, and we have the Fermi momentum determined by the chemical potential. Now, there are going to be many lines drawn here to show the tunneling and so on, so let's remove the axis and just remember that we are looking at energy versus momentum dispersion. Now we'd like to see how tunneling happens. But in order to see that, we'll introduce another way of looking at this system, which is looking just at what happens close to the Fermi points, here and here for each wire. So here are the right movers that live here. Here are the left movers that live here for wire 1, wire 2, wire 3. Now let's introduce the tunneling. An electron that tunnels starts from a Fermi point, this, and so on, and tunnels to the next wire, and along the way it accumulates a momentum from the Lorentz force. So here is how a tunneling event can look. You start from a Fermi point, and if the parameters are matched properly, then you also end at a Fermi point, but it won't be the same Fermi point, because you got momentum. So this is what happens when the momentum you get by the Lorentz force is exactly twice the Fermi momentum, which is exactly the condition for nu equals 1. So nu equals 1, the simplest of all quantum Hall states possible, is the state where you have electrons tunneling from the Fermi point on the left to the Fermi point on the right of the neighboring wire. And then another tunneling event from this left point to this right point, and then from this left one to the next right one, and so on and so forth. But you see that two Fermi points are left uncoupled. This one, which corresponds to this one, and the one on the other side that goes in the other direction. Now what happens out of this coupling? So when we couple left movers to right movers with a coupling that tunnels electrons between them and matches the momentum difference, what happens is what we know from Bloch's theorem, from nearly free electrons, approximation to Bloch's theorem. What happens is that this and this gap one another, or tunneling gap them both. So we get a gap of these 2 points, a gap of these 2 points, and so on and so forth. And we are left with only 2 gapless modes, one here and one on the other side of the sample far away down. And that's exactly what we expect from nu equals 1, right? We expect to have an edge mode going to the right on one side, going to the left on the other side. So this is how we construct an integer quantum Hall state by a wire construction. Now this is nu equals 1. We can also generalize this to nu equals 2. So in order to do that, we need to, if you look at this equation, we need to change this 1 here to 2, because this would be the condition for nu equals 2. Remember the expression we had for the filling factor in terms of K, Fermi, D, and the magnetic field. So we need to double the momentum you get while tunneling. And the way to do that without changing the magnetic field is have tunneling across 2 wires. Tunneling from here to here. And tunneling from this one to the next one. That would do exactly the same thing. It would gap modes in pairs. But this time leaving an edge mode here and an edge mode here on this side and a counter-propagating edge modes on the other side. So the nu equals 2 state, as we expect in fact, has 2 edge modes on each side of the sample. So this is how we construct integer quantum Hall states. To summarize the idea and get us ready to apply the same idea for fractional quantum Hall states, let's remind ourselves what we did. We coupled wires by tunneling. The tunneling had an electron going out some momentum of origin and getting into a momentum of destination. So an initial momentum and a final momentum. And in between, there's a difference, momentum difference, which the electron gets from the Lorentz force. And that momentum difference is E times B times D divided by the speed of light multiplied by how many wires are being hopped over in the tunneling process. Now, the crucial point is we want these tunneling events to form energy gaps at the chemical potential. And therefore, the final momentum and the initial momentum should all be at the chemical potential. And this is what we saw for nu equals 1. Not only that, we need this coupling to couple 2 modes which move in opposite directions, as exactly is seen here. And we need the coupling to be strong enough to open a gap, and that plays a larger role in the fractional quantum Hall states, where tunneling processes may renormalize as you change energies, but we'll see how the fractional case looks. Let us now use this approach to construct a fractional quantum Hall state of nu equals 1/3. So start from nu equals 1. This is the setting that got us the nu equals 1. The momentum you get from the Lorentz force is exactly 2 times the Fermi momentum. Now let's change this to nu equals 1/3. Not by changing the Lorentz force momentum, we keep the magnetic field fixed, but by changing the density. We'll reduce the density by a factor of 3. So the chemical potential went down and the Fermi momenta went down by a factor 3. So now these arrows that describe to us the momentum you get from the Lorentz force are not compatible with the requirement that you start and end at Fermi points. They are compatible if you want to start and end from where we started and ended before, but they're not compatible now. That is actually not surprising, because we know in order to get the fractional quantum Hall effect, we need to put in interactions. And we will put the interactions in order to help us tunnel from here to here, but through a virtual state from which tunneling becomes momentum compatible, or compatible with the Lorentz force momentum. Let's see how this happens. First of all, nu equals 1/3 means that you need 6 times K Fermi, or 6 times h bar K Fermi, to be equal to the Lorentz force momentum. So, you know, for nu equals 1, we tunneled from here to here. For nu equals 1/3, the Fermi momenta are here and here. How are we going to get this mismatch? By electron-lepton interaction. And the way we'll do that is the following. We apply electron-lepton interaction to scatter 2 electrons from occupied states at the Fermi energy exactly to 2 states which are 2 kF away. One goes from minus K Fermi to plus K Fermi, and one goes from minus K Fermi to minus 3 K Fermi. This is the point from which the Lorentz force momentum allows tunneling allowed tunneling in order to create nu equals 1. So we'll do that. So we'll let the electron jump to here using electron-lepton interaction in a process that conserves momentum. You see 2 kF in each direction. Does not conserve energy. It's a virtual process, right? It's a process that we will go to a higher order for virtual transitions, and gets us to the position of the momentum from which it's convenient for us to tunnel. So here is the tunneling here, and then from here now we can do the same thing and have 2 electrons, one being transferred from the left Fermi point to the right Fermi point, and one being transferred from 3 K Fermi to 1 K Fermi. So altogether, we have 3 electrons participating in this story. One went this way, one went this way, so this electron in wire 1, this electron in wire 2, and the third one had the most complicated journey. It went up to this point, tunneled, and went down. Altogether 3 electrons, altogether 2 orders of interaction, 2 interaction operators, 1 tunneling operator. But combining all this, we have a process that satisfies the requirement that we defined earlier on, which included that electrons should tunnel from a Fermi point to a Fermi point, or from this Fermi point to this Fermi point. And in this way, we couple the Fermi point on the left here to the Fermi point on the right here, and so on further down. Now, calculating the filling factor where that happens, look at let's draw this with less colors and lines. We have 1 electron going from left to right, 1 electron going from left to right, and 1 tunneling. Altogether 2 K Fermi, 2 K Fermi, 2 K Fermi, altogether 6 K Fermi, and momentum matching that corresponds to nu equals 1/3. Now we can generalize this, right? We know already from the nu equals 2 case that we can we can tunnel across more than 1 wire, and then this number will be multiplied by n. We can also have more electrons playing this game. For example, not just 1 here and 1 here, but 2 here and 2 here, or any other number. And doing this, we can generalize this procedure from just constructing the nu equals 1/3 state to constructing a whole series of fractions of the form n over 2m plus 1, which are all fractions with odd denominators. In fact, we can even generalize this to even denominator fractions in a way that I will not cover here. Now I should say, all this procedure for the fraction quantum Hall effect involves interactions. The Hamiltonian is not quadratic anymore. It has a 4 fermion terms, and we repeat, and we have virtual transitions along the way. This type of interaction renormalizes as we take energies to lower and lower values. And we need, and I will not get into those details, we need the interaction to renormalize to strong coupling so that we are guaranteed that the gap is opened at all wires except the very edge. I'm also not getting into how we analyze the properties of the edge of fractional quantum Hall states in this way, but the same property that we saw on the video of, about the edge can be reproduced using this approach. So to summarize, wire constructions give us a systematic way to construct series of fractional quantum Hall states, and to extract the topological properties, you know, charges, fractional charges, edge structures, bulk edge correspondence, various others. But it's hard to get something quantitative from this approach because we start from an anisotropic system and we are not able to account for tunneling strong enough to make the resulting system isotropic. So actually looking at quantitative numbers out of this, getting to the isotropic limit is very hard. But still, it's a way that gives us intuition and gives us insight into the topological properties. And not only that, we can use wire constructions to create interacting and fractionalized and also non-interacting topological states which are not quantum Hall states. For example, Yuval in his explanation of topological superconductivity used a wire construction to create a two-dimensional topological superconductor. So it's an approach that's of wide use. That's as far as I wanted to go about wire constructions. In the next video, we'll talk about flux attachment.